Graphs of rational functions. First of all, rational functions are where you have one polynomial divided by another polynomial. So p of x over q of x. And then whenever we're dividing by something that has an x in it, we always got to watch out for the domain. The domain being all real numbers except for the zeros of q of x, of the denominator. So they can be very complicated, very simple. Here's an example. 2x plus 3 is a first degree polynomial, a linear function, divided by a fourth degree polynomial. Here's one, 3 divided by x squared subtract 4. 3 is a 0 degree polynomial divided by a second degree polynomial. Now, one of the characteristics of rational functions that we need to look at is what we call asymptotes. The line that the graph kind of cozies up to kind of shows some of the long-range behavior of the function. So just a reminder, horizontal lines have equations in the form y equals some constant, and vertical lines have equations that are in the form x equals some constant. Okay, so exploring vertical asymptotes, if the value of x where the function either approaches infinity or negative infinity, or both, I like to think of it just where the function blows up. So if you look at f of x as 1 over x plus 2, and as x approaches negative 2 from the right, and by that I mean as x gets closer and closer to negative 2, using numbers slightly to the right of negative 2, at negative 2 itself we get an error message. At negative 1.9 the function equals 10, negative 1.99 the function equals 100, negative 1.9999 equals 1,000. Here the calculator rounded a little bit, negative 1.9999, x is equal to 10,000. This is what's happening here on the function. As x is getting closer and closer to negative 2, the y values are shooting off to infinity. Whereas over here, to the left of the line, x equals negative 2, as the values of x get closer and closer to negative 2, the value of the function is approaching negative infinity. So that's in this table right here. So x equals negative 2 is what we call the vertical asymptote of the graph. It's a characteristic of the function, helps us accurately sketch what's happening with the graph of the function. Okay. Now looking at the function again, we're going to look at what happens as x approaches infinity. So I actually did this on my graphing calculator and just traced off to the right, and as x values got larger and larger, 10, 20, 100, the y values became, 0.01, 0.001, 0.0001. Y got closer and closer to 0, but never actually reached 0 and never became negative. And then as I trace the graph and let x approach values close to negative infinity, like negative 10, negative 100, y approached 0 from below, they never reached 0 and never became positive. And so the line y equals 0 is what we call the horizontal asymptote of the graph, also known as the x-axis. Okay, so formal definition. The vertical asymptote is the value of x that makes the denominator equal 0. So to find the vertical asymptote, just take the denominator, set it equal to 0, and those are going to be our vertical asymptotes. Which also, now think a minute about it, the domain of the function is all values of x except for where the denominator is 0. So once you've found a vertical asymptote of a function, you also know something about the domain of the function. So this example here, I factored the quadratic, got two linear functions, set each of those equal to 0, solve for x, and I've got two vertical asymptotes, x equals negative 6 and x equals 1. But I also know that the domain of the function is going to be all values of x except for where x equals negative 6 and x equals 1 because the function's undefined there. I put it in my graphing calculator. I didn't get too bad of a looking graph. I think the hand-drawn graph is a little easier to see what's going on. I went ahead and found a couple of nice points. I found the intercepts. I let x equal 0, solve for y. That's get my y-intercept. I let y equal 0, solve for x, and got my x-intercepts. That gave me a couple points on the graph also. Just as a general rule, sketching your asymptotes with dotted lines, and then use a solid line for the graph itself. Okay, so this is the messy part, the horizontal asymptotes. Vertical asymptotes, pretty easy to find. Again, just let the denominator equal 0. For the horizontal asymptotes, what we're going to pay attention to is a leading term of both the numerator and denominator. So if your rational function's not written with the polynomials in standard form, highest degree to smallest, go ahead and rewrite it that way. And then what we're going to do is compare the degree of the numerator to the degree of the denominator. If the numerator at the top has a smaller degree than the bottom, then the horizontal asymptote is just going to be the x-axis, y equals 0. If the degrees are the same, like we have a second degree over a second degree, then y equal the leading coefficient over the leading coefficient is going to be the horizontal asymptote. And at the top, the numerator has a larger degree than the denominator. There will not be a horizontal asymptote, but there'll probably be a slant asymptote. Okay, so this one I have a first degree polynomial over a first degree polynomial. The horizontal asymptote is going to be the ratio of the leading coefficients, so the 4 over the 3. Y equals 4 over 3, or y equals 1 1/3. Vertical asymptote, I let the denominator 3x subtract 2 equals 0. Solve, and that gives me x equals 2/3. That also tells me the domain is going to be all real numbers except for where x is 2/3. The y-intercept, I let x equals 0, solve for y. X-intercept, let y equals 0, solve for x. Now before I actually sketch this, I took a look at all these numbers I've got and realized they're all either really close to 1 or smaller than 1. So before I did my sketch, I thought a little bit about the scale I wanted to use, and so rather than letting my grid go 1, 2, 3, 4, I expanded it out a little bit, and here's my 1, 2, 3, 1, 2, 3, so I could actually see the detail in the graph that I had. And then I usually start off with sketching my asymptotes, so my horizontal asymptote, 1 1/3, my vertical asymptote, x equals 2/3, put those in as dotted lines. I located my x and y intercept on the graph, and then I connected with a smooth curve the two pieces of the graph and have them approaching the asymptotes. I use my calculator to double check things, but keep in mind a graphing calculator in general is not going to do a nice job of graphing these rational functions. It just doesn't have the detail that you really need. Okay, here's another one. I've got a 0-degree polynomial over a second-degree polynomial. My vertical asymptotes, when I set my denominator equal to 0, I'm not getting any real solution, so there's no vertical asymptote. It also tells me the domain will be all real numbers. And then the horizontal asymptote, looking at the degree of the numerator, it's smaller than the degree of the denominator, so y equals 0, the x-axis is going to be my horizontal asymptote. Went ahead and found my x-intercept and y-intercept. Turned out there were no x-intercepts, and had y-intercept at 4. Graphically, I get this kind of bell-shaped curve. It's a rather nice-looking curve. Okay, this example is actually one I just pulled off of one of my old tests. So if you're studying for a test, this is something to maybe pay attention to, and how I might write the instructions. So I want a detailed graph. I want an appropriate scale, dotted lines to show the asymptotes, show any intercepts, list all the characteristics, and don't forget to write x equal and y equal for the equations of the asymptotes. So I factored my numerator and denominator, set the numerator to 0 to get my intercepts, set my denominator equal to 0 to get my vertical asymptotes, which also tells me something about my domain, compared the degrees, y equals 3 over 5 will be my horizontal asymptotes, and did my sketch.